This is part 3 of lecture 6. We are discussing how to overcome the limitations of the basic difference amplifier. In part 1, we discussed how to overcome the limitation of low input resistance. In part 2, we discussed how to enhance the gain of the basic difference amplifier. And in part 3, we'll see how we can overcome the third limitation, that is the difficulty in varying gain of the basic difference amplifier. And finally, how we can develop the modified difference amplifier, which is known as the instrumentation amplifier. This is our modified difference amplifier circuit that we developed in the part 1 and part 2 lectures of the lecture 6. And in this modified difference amplifier circuit, we have the two stages. One is the input stage and the other is the output stage. The output stage is our usual difference amplifier with gain R2 by R1, and the input stage here we have the two non-inverting amplifiers, and these two non-inverting amplifiers, they not only add gains to the basic difference amplifier, they also provide infinite input resistance, and that is how we overcome the two limitations of the basic difference amplifier, that is the low input resistance and the low gain. Now the third problem that we still have is the difficulty in varying the gain, how we can solve that problem. At first look, it looks quite uh, complicated, or is not clear how we can solve that problem. But a little tweaking in the circuit and intelligent tweaking can solve that problem. If you look at the circuit here, the two resistors R here and R, they both are going to ground. They are connected to ground. That means they are connected to the same node, same point. And that we can show like this. These 2 points basically connected together. And what if we combine them, these two R's, into one single resistor? How the circuit will look like when you combine these two. This is how the circuit will look like once you combine the two R's into one single R. Now here we have this one single piece of resistance R that is connected between the two inverting input terminals of these two op amps. Now this is little bit different from our well-known non-inverting amplifier configurations. Op amp 1 and op amp 2 are not the exact same non-inverting amplifiers as we know, because R here is not grounded, and we have one piece of R that is connecting these two terminals. Now the question is, what will be the overall gain of this amplifier, and will it be possible to vary the gain if we vary R, because there is only one single piece of this resistance R. So in order to answer these questions, so we have to look the gain expression. We need to determine what will be the gain expression. So like before, we can express the gain as the product of the two gains. The first term here is the gain expression for the output stage, what is also known as the difference amplifier. So the output stage gain for the well-known difference amplifier circuit. The second term here, that is the gain expression for the input stage. The output is V02 minus V01 and input is V2 minus V1. So that is the gain of the input stage. So now we need to determine what will be the gain of this input stage, because the gain of the output stage is already known. So now we'll try to determine a gain expression for the input stage of this modified difference amplifier circuit. So basically we try to evaluate this expression, the gain expression for the input stage. Now what will be this? How do we determine this? So in order to determine this, what we need to do, first we need to determine an expression for this voltage difference V02 minus V01. And how do you do that? We know the resistance, the total resistance that we have from this point to this point. Then in order to find the voltage, you need to know the current. And if you can multiply the current with the resistance, then you got it. Then you have found the voltage. How do you determine the current? Right? So current is the voltage difference divided by resistance. So again, but we are trying to determine the voltage difference here. So that is unknown, but what is known, the voltage at this point at the inverting input terminal of op-amp 1 and the inverting input terminal of op-amp 2. So these two voltages are known. So how do you know these voltages? Because of the virtual short circuit condition. Because of the virtual short circuit condition, you see that voltage at this terminal will be same as the voltage at this terminal. Same can be said for op-amp 2, the voltage, whatever voltage we have at the non-inverting terminal, the inverting input terminal will also have the same voltage. So that means we have voltage V2 here, same as V2 at the non-inverting terminal, and also voltage V1 at this end, same as the voltage V1 at the non-inverting terminal. So with this, now we know the voltage difference across this resistance R, and if you divide that voltage difference, by the resistance R, you get the current I, how much current will flow through R. Now we have determined the current through R. Now we need to determine what current will flow through these two RFs, and that is also very easy to find out because the current through the other branch is 0. See, the other branch here is the going into the op-amp, and ideal op-amp has infinite input resistance and the current will be always 0. So this current I has only one path to flow, that is through this RF here and through this RF. So this is how the current will flow. First through RF it is coming towards the R, and then it flows out through this RF. Now we know the current that is flowing through this series combination of these three resistors, and so we can determine the voltage difference V02 minus V01 is the current times the resistance. So that can be, we simplify to this, and then we substitute the expression for the current I. I is just as we have said, is the voltage difference divided by this resistance R. So that is our current I. And now if you simplify the expression, take R inside, and this we can write like this. So now we have the voltage that we were trying to determine. We have expressed this voltage in terms of the input voltage V2 minus V1, and rearranging the terms of this expression, now we have got the gain expression for the input stage, what is 1 plus 2 RF by R. So now that we have determined the gain of the input stage of the modified difference amplifier circuit, we can determine the overall gain of this modified difference amplifier. And the overall gain, as we have already expressed in our previous slide, is the product of two gains. One, the first part is the gain of the output stage, that is our basic difference amplifier, and the second part here is the gain of this input stage, and that we can express like this. So that is the gain of the output stage R2 by R1, and that is the gain of the input stage 1 plus 2 RF by R. And if you look at this expression here, this gain expression for the input stage is even higher than that of the circuit before modification, before combining the two R's of the input amplifiers into one single R. The gain of that input stage before that modification, before the combining two resistor into one single resistor, was 1 plus RF by R. Now, after combining the two resistors, after replacing the two resistors by one single resistor, now gain is 1 plus 2 RF by R. That is almost twice as much as we had before. So gain is even higher when we replace the two resistor by a single resistor. So with this modification of the difference amplifier circuit, replacing the two R's by one single R, we get a gain that is even higher than our gain before the modification of the circuit. We had RF by R, now we have here 2 RF by R. Not only it increases the gain, it also makes it possible to vary the gain easily, because if you look at this gain expression, we have this R here in the denominator, and we have only one single piece of R in this circuit. So if you vary the R, this one single piece of R, which we can easily vary, then we can vary the gain, and you don't have vary two resistors at the same time. So this will overcome the limitation of the difference amplifier, where it was difficult to vary the gain because we had to vary two resistors at the same time. So now with all these modifications that we have done till now, we are able to overcome all the three limitations of the basic difference amplifier. We have solved the problem of low input resistance. This modification now provides ideally infinite input resistance at these non-inverting input terminals, and we have substantially increased the gain, because now the gain is the product of these two gains, and it is possible to achieve very high gain with this modification. And we have also solved the problem of difficulty in varying the gain. So we have successfully solved all the three problems of that the basic difference amplifier suffers from: the low input resistance, low gain, and the difficulty in varying the gain. But one small problem remains with this modified circuit, and what is that? If you look at the gain expression of this modified circuit, the gain expression in the denominator we have R, a variable R, and a variable R, like a potentiometer, you can vary the resistance from 0 to some maximum value. Let's say you take a 10K resistor, then you can vary the resistance from 0 to 10K. So now what happens here? You are varying the resistance to vary the gain. Now if you hit the 0, if R becomes 0, so what happens? Gain becomes infinity. You get a short circuit. When R is 0, that means you get a short circuit, and that will put you in trouble, that you might damage the circuit. whenever there is a short circuit, it might damage your circuit. So you need a solution for that, how you can avoid being short circuited. So in order to avoid short circuit, what we do, we put a small fixed resistance in series with the variable resistance. So now R, instead of just one single variable, will be composed of a fixed resistor in series with the variable resistor. So when the variable resistor, if it becomes 0 at any point of time, if it becomes 0, the resistance R will be Rf. So R will not become 0, even the variable resistor, the resistance becomes 0, and the gain, the overall gain will become this. So in the denominator we have now Rf when variable resistance becomes 0. So you don't have the short circuit and gain does not become infinity. With this modification, now the overall gain of this the overall gain of this modified difference amplifier, we can express like this. That's in the denominator, instead of R, we put Rf plus Rv. So we have a fixed resistor in series with the variable resistor, and that we show in the diagram like this. We have the fixed resistor in series with the variable resistor Rv. So this Rv can hit 0, it can become 0, but still you have Rf, and you can avoid short circuit at any point of time. So with this modification, now you are able to vary the gain of the overall circuit, the modified circuit, from some minimum value to some maximum value. The gain will be minimum when the RV, the variable resistance value, will be maximum. Let's say you have a 10K pot, so when the resistance is 10K, resistance is maximum and the gain will be minimum. So that we express like this, the minimum differential gain, and the gain will be maximum when your variable resistance RP is 0, and that we express like this, the maximum differential gain is this with RV 0. So this modified circuit is known as the instrumentation amplifier, that is widely popular in the industry, and this is uh, because of this popularity and because of this all desirable features that we look for in a good amplifier, this circuit is constructed as one single IC chip like op-amp. Like op-amp comes in a single IC chip. Similarly, the instrumentation amplifier with 3 op-amps also is fabricated and is available in the market as one single IC chip. So that is our final fully developed modified difference amplifier circuit, which can overcome, or which overcomes all the limitations of the basic difference amplifier circuit. It has 2 stages. One is the output stage, that is our basic difference amplifier circuit, and the other is the input stage, which is used to overcome the 3 limitations of the basic difference amplifier circuit. The circuit as a whole is known as the instrumentation amplifier, and it has these advantages: that it has very high input resistance, ideally infinite input resistance. It has a very high gain. The gain is the product of these two gains, and it is possible to achieve very high gain. with this configuration, and it is also very easy to vary the gain because we can just vary one single piece of resistance here and we can easily vary the gain.